this subset or outside of this subset. And also, if you take the intersection between this and this, it's empty. It's trivial, right? So if you take the intersection between this part, inside this part, and outside this part, there's no overlap, so the intersection should be empty. So that means if the subset A is U itself, then its complement must be empty. Okay? If you have, where is it? So if the entire universe is your subset, then its complement is nothing. So it's empty. Okay? So this is a related concept, relative complement or set difference. Okay? Actually, the previous complement, this complement is a special case. This complement is a special case of this one. Okay, let A and B sets. The relative complement of A in B, denoted by this, is the set of elements of B which are not in A. Okay, that is, this is defined by this, that is subset of B which is not part of A. Okay, so let's say this is a universe, this is B, and this is A. Okay, so this set difference, relative complement of A in B, is a part of B. Maybe I should use this one. Part of B, excluding part of A. Excluding part of A. So this is B, but excluding part of A. So that means this means so this means this part. So that's the set difference. Okay, relative complement or set difference. So in the case of previous complement, this complement is just a special case of this one, where B happens to be the entire universe. B happens to be entire universe. Okay? Now, here's one theorem. Theorem. Let A and B be sets. Then the following statements are equivalent. 1. A is a subset of B. 2. A intersect B is equal to A. And 3. A union B is equal to B. So, do you know the meaning of equivalent? This is a technical term. Okay. So let's say we have two statements, P and Q. If they are equivalent, that means if P is true, then Q is true. And if Q is true, then P is true. Okay? So in this case, these three statements are equivalent. That means if this is true, then this is true. And if this is true, and this is true. If this is true, then this is true. And vice versa. Converse is true. And if this is true, this is true. This is true, this is true. Okay? So that means what we want to prove is that assuming this is true, prove this is true and this is true. And assuming this is true, prove that this is true and this is true. And assuming that this is true, prove that this is true and this is true. That's what we need to do to prove this theorem. Okay? So let's do it. So first we prove this. This means we assume this is true, then prove this is true. So therefore, assume this. Suppose A is a subset of B. Then, taking the intersection of both sides with A, we have this. Why is this true? Can anyone say that? So we assume this is true. Okay, so this is given. Now we take intersection of both sides with A. So intersection with A is this. Intersection with A with B with A is this, right? So if this is true, this is true. But is that right? Really? How can you say? Remember the previous lemma? Lemmas are used for proving theorems. So let's go back to the lemma. Where is it? Look. A, B, X, and A is a subset of B. Oh, I forgot to put equal sign here, but then let's say, okay, so if this is the case, this is true, right? We proved it. So let's say this X happens to be equal to A. Then that means A intersect A is subset of B intersect A, right? That is exactly where is it? This. Exactly this. So this is by lemma. Right? So this is okay. But A intersect A is just A. And A intersect B is a subset of A. Is this okay? You know, if we have A and B, intersection is this one. So this is completely included in A, right? So that means this. So, okay. From the previous page, we have this one. So we have this, right? But this is equal to A. And this is a subset of A. Okay, so this is a subset of A. But here we have A and A, right? So if you look at this one, then A is a subset of A intersect B. And if you look at this part, this A intersect B is a subset of A. So that means this and this are equal. Right? I mean, that was the definition of equal for sets. Right? By the way, this means this, right? So, oh, wait a minute. Wait a minute. This is a typo, I guess. This is intersect. So this means A intersect B is equal to A. Okay? So by this we have proved from here to here. But we also have to prove the opposite direction. You know, the converse may not be always true, so we have to prove it. So suppose, oh, again, sorry for many typos. Suppose A intersect B is equal to A. Then this is trivial, isn't it? Is that okay? So what does this mean? A intersect B here is completely equal to A. So that means there is no such part like this one. But it must be like this one. So this part is A. This is B. So if A intersect B is equal to A, it must be that A is completely included in B. Completely included in B. Therefore, this is trivial. Okay? So that's all I show for this theorem. And the rest is your exercises. Exercise, right? Okay, so what you need to do is assume 1, then prove 3, vice versa. Assume 2 and prove 3, and vice versa. Okay, that's exercise. But you can use the similar technique